Hello everybody, my name is Ryan and I am a TA for Chem 101. I'm very excited because we're going to do this in one take perfectly, I hope. We have before us a good time, I think. So what I'm going to be doing is I'm just going to go through the Exam 3 review sheet. Dr. Watt, I think, emailed it out to most everybody. It's also available in Learning Suite under the Content tab, and then you go to the Reviews section. This should be review number 3. I'm just going to go through each point. I'll talk about definitions. I'll do an example problem for some of the points, and we're just going to go till we're done. So hopefully this goes well. Okay, our first topic is balancing equations. So in this, we need to be able to take an unbalanced equation and balance it so all atoms are equally represented in the equation. That's what the review sheet says, I think word for word. I just read it to you. But we need to be able to balance things so that we conserve atoms on both sides. In the equations that we talk about in this class, we don't destroy atoms, we don't create new atoms, we're just balancing things. So an oxygen atom that we had at the beginning, we need to have that oxygen atom when we finish. So here's an example. Let's say I have magnesium fluoride and potassium nitride, and we swap and we produce potassium fluoride and magnesium nitride. So I'll write that for you. We got magnesium and fluorine. Now because magnesium in an ionic equation it has a 2+ charge, fluorine has a 1-, we need 2 of those. And then we add potassium nitride. We have K and we have N here. And because N typically has a 3- charge, potassium has a 1+ charge, we need 3 potassiums to balance that out. Then we produce potassium fluoride and magnesium nitride. This is a double replacement reaction. We're going to talk about that in more detail in a little bit, but we'll write down the formulas for the compounds we produce. So we make potassium fluoride. This is a charge of -1. This is a charge of +1. Our formula is just fine like that. And we also produce magnesium nitride. So we'll have Mg and N. Now to balance a charge of 3- and 2+, we'll just swap the charges in the subscripts. So this 3 will come down here to the magnesium. And the 2 of the charge of the magnesium will come down here to the nitrogen. So we've written all the correct formulas here, but this is not balanced, right? If I wrote down, say, each type of atom we have Mg, we have magnesium, we have fluorine, we have potassium, and we have nitrogen. On this side of the equation, we have 3 magnesium, 1 fluorine, 1 potassium, and 2 nitrogen. If we come over here to this side, we have, sorry, I gotta write it down here real quick. We have 1 magnesium, 2 fluorine, 3 potassium, and 1 nitrogen. So we somehow apparently gain magnesium as we go across there. This is a good sign that our equation here is unbalanced. Typically what I like to do is I just pick something that's in only one compound on both sides of the equation, and I'll just balance that first. Really, your pick of whatever you choose to balance first, it doesn't really matter, just as long as you carry it through and you're consistent as we continue throughout the rest of the problem. So I'm going to balance magnesium first. I know that I have more magnesium over there than I do over here. So we have 3 magnesium right there. We only have 1 in this. If I put a coefficient of 3 in front of this formula, that will give me 3 magnesium atoms. That's great. That means magnesium is now balanced. But that does change the total number of fluorine atoms that we have, right? We had 2 at the beginning, and now we have 3 times 2 amount of fluorine atoms. That's going to give us 6 fluorines. So now we've balanced magnesium. I guess we could just go ahead and balance fluorine. So we have 6 fluorines over here and only 1 over there. And that means if I put a 6 in front of this molecule right there, that means now we'll have 6 fluorines, which balances our fluorines. This does change the amount of potassium that we have over here. Now it's 6 potassium. We could balance our potassium next. I think that's pretty convenient. Doesn't really matter if we do potassium or nitrogen. We're going to get to a similar answer. We have 6 over here, and we have 3 potassium over there. Conveniently, if we double the amount of potassium over there, we'll have the same amount on both sides. So let's go ahead and do that. If we put a 2 right there, that'll be 2 times 3, that's 6 potassium, which is the same amount as on the other side. That also changes the amount of nitrogen that we have. That's 1 times 2 now, so there are 2 nitrogen. And hey, would you look at that? We did it! That feels good, huh? I hope it does, because you do this a lot. We can tell that our equation is balanced and as simplified as possible if we look at all of the numbers in front of our formulas, and if there is at least one number that is odd, or like this one is blank, that's just a 1, right? If there's at least one of them that's an odd number, then it's as simplified as possible. Because in theory, I could multiply all of these by 2. So like, we could have 2 right there, and a 12 right there, and a 4 right there, and a 6 right there. Technically, if we had those numbers, this equation would still be balanced, right? But it wouldn't be simplified. It wouldn't be as simple as we could get it. It wouldn't make our math as easy as possible. We like everything to be as easy as we can get it. And to do that, we would need to divide all of these by 2 to get them as simple as we can get. So that's what balancing an equation is like. You pretty much make sure that you do this before you do pretty much everything else in all of the other problems that we're going to expand on. You need to have a balanced equation because this is kind of like it's like your basis. So let's move on. We're going to talk about types of reactions. So I'll erase some things, but I'll leave the equation up because I think it's a pretty good example of a few things. So I mentioned that this is a double replacement reaction. I'll give you a look at a single replacement reaction, and then we can talk about what a double one is. So a good example of a single replacement reaction would be, say we have potassium plus sodium chloride, and then those react to produce sodium plus potassium chloride. You'll notice that there's one of each type of atom on both sides. This is balanced. We don't need to worry about it. Feels good. In this reaction, we're taking a compound, sodium chloride, and we're introducing potassium. This potassium takes the place of sodium in our reaction, so we produce potassium chloride, and then we have sodium that just kind of gets booted out to the curb, right? This is called the single replacement reaction. We just pretty much replaced one thing in the reaction, that's why it's called that. So if I said you have potassium and sodium chloride and you have a single replacement reaction, you could figure out what your products will be. You know that potassium forms positive ions, and sodium here is a positive ion. If this is a single replacement, potassium will have to come in and replace one of these things. Potassium will have to replace sodium because potassium only forms positive ions. Unless you, we're not going to talk about weird edge cases. So we know that potassium would come in to be with chlorine, like that, and then sodium is conserved, and it just kind of is hanging out here on its own. Double replacement is kind of like this, except we're doing it twice, right? Here we have magnesium fluoride, and we have potassium nitride. In theory, what we're doing is we're just swapping the positive ions, or the negative ions. It doesn't really matter, just as long as it's just one of them. So you could say magnesium is going to replace potassium, and it's going to end up with nitrogen. And potassium is going to replace magnesium and end up with fluorine. And that's exactly what happens. If I said that this was a double replacement reaction, and I gave you those two products, you would know that potassium and magnesium were the positive ions. They'll switch And so you'll say potassium will go with fluorine. And because those charges are already balanced, that's our formula. And then we know it will also produce magnesium nitride. And just like we did at the beginning, we'll have to balance those charges. So we'll have 3 magnesium and 2 nitrogen. That's 2 times -3, -6 total negative charge, and 3 times 2 plus 6 total positive charge. That balances out, net charge is 0. I think this coefficient was a 6 earlier, if I remember right. So this is a double replacement. This is a single replacement. Let's talk about a few other examples. I think we have there's combination and decomposition. They're basically the same thing, but in reverse. So let's say we have magnesium and we have oxygen, and they are in a combination reaction. What that means is we take 2 things and we smush them together. I feel like it's pretty intuitive. And because the charge on this is generally a 2 plus and the charge on oxygen is generally a 2 minus, our formula over here will be MgO. Now, this is not balanced. That should concern you. I'm just going to look at this. We have 2 oxygens on this side and only 1 over there. If I put a 2 right there, that balances our oxygens. Now we have 2 magnesiums over here and 1 over here. If I put a 2 right there, that balances the magnesiums. We're balanced. Feels good. Can't be any simpler because there's just a 1 coefficient in front of this O2. So this is a combination reaction. Now imagine if instead of the arrow pointing that way, we had the arrow pointing this way, like this. What that's saying is magnesium oxide over here is our reactant, and then magnesium plus oxygen gas, those are our products. This reaction would be a decomposition reaction. Basically, you're taking something that is the combination of two or more things, and we split it into the parts. I hope that makes sense. So that's why combination and decomposition are kind of inverses of each other. Now there's one more type there's 2, but one of them that we'll talk about is combustion. So let's say you are burning some fuel, you want to cook some hot dogs, I suppose. You'll take your fuel, which in our case is CH4, I think that's methane? I think so. And then we add oxygen, right? Fires need oxygen to burn. Yes? Is it too high? I've been informed by my trusty editor that I am writing too high on the board. I'll bring it down. All right, so we have CH4 right here plus O2 to burn it. And then if you burn it, it reacts and it forms some different products. We always form CO2 and H2O. This is a combustion reaction. You can think of it like we do this technically with sugar in our bodies. That's how we produce energy. We breathe in oxygen and we eat food, which is this fuel. It's going to be some bunches of carbon and hydrogen. And then we breathe out carbon dioxide, and there's some moisture in our breath as well that we breathe out. So this is a really important type of reaction. We do this all the time. Oftentimes with these equations, of course, you'll see little symbols afterwards that will tell you like what state of matter they're in. I often leave them out, but on the exam, definitely write all of those in. CO2 is a gas. O2 is a gas as well. I think this is a gas as well. Sodium chloride, that's a solid unless you've dissolved it in water, for example. So yeah, that is a combustion reaction. You can pretty much always identify it. It's going to be something with C and H at the beginning. The numbers might change. You might even have some oxygens in there. It'll react with O2 gas, and it will form carbon dioxide and water. That's how you identify a combustion reaction. Now there's one more type that you've heard about. It's called oxidation reduction type reactions. There are a few definitions for oxidation or reduction. which can make them kind of confusing. I'm going to talk about them, but there's one definition that's more important, the most important of all the definitions. If you remember oil rig, I think I'll erase this as well. Oil rig, it's kind of a handy little mnemonic. I'll write it for you. This stands for oxidation is loss, reduction is gain. This is referring to electrons. So what it's saying is something is oxidized when it loses electrons. Reduction is when it gains electrons. So let's actually look at this equation right here. This is a great example of an oxidation reduction type equation. So this is a double replacement, but it can also be an oxidation or reduction. Oxidation reduction happens in other types of reactions as well. So here at the beginning, we have magnesium, which is a 2+, and then it becomes a 2+ over here. I actually started this and realized it was a bad example. I'm sorry, you have my apologies. However, we're doing this in one take, so I'm not starting over. The reason why this is a bad example is because all of these ions have the same charge before and after in this equation. So what that means is no electrons are gained or lost by any of the ions. This is not an oxidation or reduction type equation. One of them that we wrote down earlier is though. We have potassium plus sodium chloride becomes sodium plus potassium chloride. Now, if we look at charges here, potassium here at this stage is neutral, has no charge, has the same number of protons and electrons. Sodium, however, does not have that. Sodium in this state, because it's in an ionic bond with chloride, this sodium ion is a +1 charge. And the chlorine has a -1 charge. That's, again, just due to the ionic bond. Now, if we come over here, sodium is no longer in an ionic bond, and it's neutral now. So there's no charge on it. Whereas potassium has become charged. It's in an ionic bond. So now potassium is a +1 charge, and chlorine is a -1 charge. So let's look at potassium, sodium, and chlorine and just figure out if they were oxidized or if they were reduced or if they were neither of them. So let's start with potassium. Potassium originally had no charge, and now it has a +1 charge. In order to become a more positive, right, to have a charge become more positive, you have to lose electrons because electrons have a negative charge. So potassium, because it became more positive, lost electrons, which means it was oxidized. Sodium, on the other hand, has a +1 charge and then becomes neutral. In order to become more negative in charge, or to go to neutral from positive, you have to gain electrons to balance out that positive charge, right? So, because sodium went from positive to neutral, that means it gained an electron, which means sodium was reduced. Now, if we look at chlorine, chlorine has a -1 charge on both sides of the equation. That means there was no change in the number of electrons for chlorine, which means chlorine was neither oxidized or reduced. This is kind of a good example of how you would do this type of equation generally. There's another type of definition for oxidation that has to do with gaining hydrogens and losing hydrogens, or gaining oxygens and losing oxygens. That's generally the case for a reaction in which there are covalent bonds. Like, let's say exactly like the combustion reaction that we had previously. CH4 plus O2 makes CO2 plus H2O. So that's not balanced. If I put a 2 right there and a 2 right there, I think we're all good to go. Yes. So in this reaction, none of these have charges, right? They're all just neutral atoms. That's why we have the other definitions of oxidation and reduction. For them, oxidation is either loss of hydrogen or gain of oxygen. This is meaning if you have a hydrogen atom bonded to you and then it's no longer bonded to you at the end, then you've been oxidized. Or if you didn't have an oxygen atom and you gained a bond to an oxygen atom, you were oxidized. The opposite is true for reduction. Oh, let me erase that real quick. So, for example, let's see, CO2, let's just look at carbon in this equation. Carbon has hydrogen at the beginning, and at the end, it's lost the hydrogens. That means it's a loss of H, it's oxidization. You could also think of it as at the beginning, it's not bonded to any oxygens, and at the end, it has gained oxygens. That also would help you know it's oxidized. If we were looking at, say, hydrogen in this equation, hydrogen at the beginning is not tied to any oxygen, but at the end, it has been bonded to some oxygen. That means that the hydrogen has also been oxidized. You could also even just look at the oxygen, right? At the beginning, the oxygen was not connected to any hydrogen, but at the end, it was bonded to some hydrogen. That means the oxygen technically gained H and was reduced. This definition, all this stuff that I just talked about with covalent bonds and reactions like this, much less important to the electron definition that I talked about previously. This one about oxidation is loss of electrons and reduction is gain of electrons, oil rake. If you only remember one definition of oxidation reduction, remember that one. Okay, so we're gonna move on here. I gotta wake up my computer. It's falling asleep on me. Let's talk about the mole. So the mole is just a number. It's not any unique quantity, it's just a number. Like if we said 1 or 2 or a dozen or a mole, like those are just all numbers. A billion is a number. A mole is just similar. It just happens to be a number that's really useful. So a guy named Avogadro came up with this. He figured out that if you wanted to have, he was like, man, what's a way that we could come up with measuring the amount of grams enough that we could know exactly how many atoms were in it. And he figured out that 1 mole of any type of atom will be a certain amount of grams. That amount of grams will be the same as the element's atomic mass in AMU. We haven't used many AMUs. Don't really worry about that. Just know that a mole is just a certain number of atoms that will give you a certain mass. When you look at the periodic table, all of the average masses underneath elements, so like if you look at hydrogen on your periodic table, there's a number underneath it that says 1.0079. You can know that 1.0079 grams of substance is equal to 1 mole of hydrogen atoms. If we go to a different element, say carbon, the number under there is 12.011. We know that 12.011 grams of carbon is equal to 1 mole of carbon atoms. I'll tell you the number that a mole is specifically. 1 mole equals 6.022 times 10 to the 23rd number of atoms. I'm relatively sure that this number is on your equation sheet, but there it is. I hope you feel familiar with it. Here's a little example problem. Let's say that we have 2.5 moles of hydrogen. How many atoms is that? Well, we can use the number we just talked about. We know that for every mole of a substance, we have 6.022 times 10 to the 23rd atoms. Now, if I wanted to, I could flip the atom so it was on top, or I could flip it to make sure the moles are on top. You do this whichever way you want, just to cancel out the units that you don't like. So here we have moles on top. I want moles on bottom. So I'm going to times it by 1 mole times 6.022 times 10 to the 23rd atoms. I'm going to trust that you can plug that in the calculator and get an answer, because I don't want to do it, but that's how you would do it. If you needed to go backwards, let's say you had 4.9 times 10 to the 19th number of atoms of hydrogen, we would need to use that number the opposite way, right? We want to cancel out number of atoms and go to moles. So I would put 6.022 times 10 to the 23rd atoms in 1 mole. And then if you divide this number by that number, you'll get your answer. Make sure that you do this in parentheses like this. A lot of times calculators, you'll try to divide by this whole number, and you'll accidentally only divide by 6.022, and then you'll multiply the top by 10 to the 23rd. So when you divide like this, be careful to do parentheses. Okay, let's keep going. When we're looking at equations, I guess we could just keep using that same one. I've been getting a lot of mileage out of that. Actually, hang on, let's see. We're gonna do some different examples. So if we have an equation, potassium plus sodium hydroxide. Hopefully you remember hydroxide. That's one of our polyatomic ions that we memorized. And this is just a single replacement reaction, so we produce potassium hydroxide and sodium. I wish that there were coefficients on these, but the numbers that we put on these previously, I'm going to change this to magnesium, so we have a better example. It's going to put a 2 there and a 2 there. Okay. So the numbers that we have here, these are just ratios. Like imagine that we put in only 1 molecule of magnesium hydroxide. That means for every magnesium hydroxide molecule that we put in, we have 2 potassium hydroxide molecules. So moles are really useful because if we can convert to moles, a mole is just a number of atoms or molecules, right? That means that we can just use these ratios to convert between them. We can't do that with grams or mass or anything because that's not stable between each of these quantities. Like if we had 45 grams of magnesium hydroxide, that would be way fewer molecules than if we had 45 grams of just potassium, right? So that's why we need to convert from grams to moles and eventually from moles to grams again. Is this because we need to be in a number of molecules in order to use these ratios. So let's see. We'll do an example here. So let's say that we have, just like this, we have 2 moles of, I'm going to change it slightly. We have 2 moles of calcium hydroxide. No, I'm going to do nitrate. I'm sorry, I keep changing my mind about these examples. So if we have 2 moles of calcium nitrate, imagine that somebody asked us how many moles of just calcium we had in there. So in our formula, there's no subscript here. That just means there's 1 calcium atom in every molecule of this. So we just do 2 moles times 1. We have 2 moles of calcium. But now if we look over here, right, imagine that somebody asked us, how many moles of nitrate do you have? We have 2 nitrate kind of groups for every molecule, right? So we would need to do 2 times 2. We would have 4 moles of nitrate. Now imagine they asked us how many moles of just nitrogen we have. Again, there's 2 of this group, so we do 2 times whatever this number is. With nitrogen here, it's just 1, so 2 times 1 times 2. We have 4 moles of nitrogen. Now, if somebody asks us how many moles of oxygen we have 2 moles of the molecules. We have 2 of these little subgroups per molecule, and we have 3 oxygens per subgroup. So we would do 2 times 2 times 3. I think that is 12 moles of oxygen. Hopefully that makes sense. Let's do another example problem of a different type up here. I think I wrote down a few. Yes. So let's say that we have let's say that we have 44 grams of magnesium hydroxide. How many moles of magnesium hydroxide do we have? Well, we can take our initial amount here, and then we use something called a molar mass. A molar mass, just like we talked about with the periodic table quantities, it's kind of a sum of all of those quantities for a certain molecule. So in magnesium hydroxide, if we wanted to count how much mass there was in 1 mole, we would count the mass of each individual atom in the molecule. So because we want to convert from grams to moles, we'll have an amount of grams on the bottom, and we'll have moles on the top. It'll just be 1 mole, because that's simple. And then we'll take all of the molar masses of each individual atom and we'll add them together. So we have 1 magnesium atom. So that's 1 times, and then we look up on the periodic table the molar mass of magnesium, 24.305, plus, because we have 2 of these groups, we need to times 2 by each of them. So 2 times oxygen's mass, which is 15.999. You could call that 16 if you like. I like my tiny amount of accuracy, so I guess I leave it like that. Plus 2 times the other type of atom, which is hydrogen, 2 times 1.0079. These are just the numbers you pull right off of the periodic table. So if you add all those up together and you divide this first thing by whatever that sum is, then we'll get our answer in moles. You can plug that into a calculator. I did earlier. I think you get about 0.75 moles. My editor has confirmed that is correct, which is good news for me. Okay, let's keep moving on. We're now around about 7.7, I think. So let's do an example problem. We have magnesium oxide produces let's go the other way, actually. That'd be more fun. We have oxygen plus magnesium produces magnesium oxide. Just to balance this real quick, we need to slap a 2 right there and a 2 right there. This type of reaction, just as a review, this is a combination reaction. Now let's say that we do this reaction and we produce 45 grams of magnesium oxide. How many grams of oxygen did we start with? So we'll start with this number, 45 grams of magnesium oxide. We'll multiply this by the molar mass of magnesium oxide with the grams on the bottom so that the grams will cancel out, like this. This amount should be, we'll look at our periodic table again. Mg is just 24.305. There's only one of them, so we just have one, plus oxygen, which is 15.999, and that produces 1 mole. Then we'll multiply whatever number we get by our ratios. So we could think of this as 1 mole of magnesium oxide. Now, to know how many moles of oxygen we produce from 1 mole of magnesium oxide, we'll need to use ratios in the equation. We could think of this as multiplying by a conversion factor. We know that for every 2 moles of magnesium oxide we produce, we use 1 mole of oxygen molecules, right? So we could write that as like this: 2 moles MgO for 1 mole of O2. And the moles of magnesium oxide will cancel and we'll be in moles of O2 now. Now we just use our molar mass to go to grams of oxygen. So we'll want moles over grams, or moles. We have a quantity, that has moles and grams. To cancel out moles, we'll have moles on the bottom. We know it'll be 1 mole. So then we'll figure out the molar mass of oxygen. Again, we'll just use the periodic table values, 15.999 times 2, because there are 2 atoms in the molecule. And then we'll just be in grams of O2. I think once you pull all of this out, I wrote down a number, you should get, I think, 17.863 grams. Should be your answer. I'll write it down for you. Okay. So that's how you do a problem like that. Doing this is something that you will do several times, and you'll kind of do variations on a theme, where we'll throw in gas laws and other sorts of fun stuff later. But you'll get lots of practice doing that, and that's a really important skill on the test. So let's keep going. Let's talk about limiting reactants and percent yield. So my favorite analogy with this is like chips and dip, right? Say you have like a small container of dip and you have a really big bag of chips. When you start to eat them together, you're going to run out of one of them first. And once you run out of one of them, you're probably going to stop, unless you're kind of weird and you like just like scooping up guacamole in your hand and eating that raw, but that's strange. Anyway, that's what limiting reactant problems are like. So let's write down an example. I think this is 7.9. Yes. Okay. So we have potassium and we have fluorine, and together they're reacting to form something. Fluorine is one of the diatomic gases, right? And when you add them up together, K has a positive 1 charge, fluorine has a negative 1 charge. To balance this real quick, we'll add coefficients there. So let's say we start with 44 grams of potassium. And then we also start with 25 grams of F2. Imagine that we react all of these amounts together. How many grams of potassium fluoride are we going to produce? So if we convert these to moles, right, so that we can compare the number of molecules. So we'll have 44 grams of potassium times the molar mass of potassium, 1 mole K. I don't have this one memorized. I have it written down though. 39.098 grams. This should give us some number. We'll do the same thing over here with fluorine. 25 grams times the molar mass of fluorine. I think it's 18.998. $18.998, and we multiply this by 2 because there are 2 fluorine atoms, right, like this. And that will give us some number. Now, you could look at this, and if you compared these two numbers, You'd be close, but you have to be careful. In our reaction, there's a coefficient in front of potassium. That means we'll need twice as many potassium atoms as molecules as we'll need fluorine atoms. So what you should do next is you should take this number, whatever number of moles you got with potassium, divide it by 2 so that you can compare base quantities of potassium and fluorine. If fluorine had a 3 right here, you would divide whatever number we got right here by 3 so that we could compare them in just basic amounts. So now, once we've done that, editor extraordinaire, did you get numbers for these?
I did, but I did it in grams.
You did it in grams?
Yeah.
Oh, okay. Well, I think I calculated it earlier. I'll look it up real quick. I could also plug it in, but I'm rather lazy. So, if we divide this by 2, this number, then we'll get 0.562, I guess, 7 moles of potassium. And then this number will be 0.65796 moles of F2. I gave you way more digits of accuracy than we started out with. Just do sig figs at the end. So now that we're in base quantities, we can compare them. We know that the potassium is going to run out first. So in a sense, we're going to have some leftover moles of fluorine. If you wanted to figure out how many leftover moles of fluorine we would have, we could just take this number minus this number times whatever coefficient was there before. So like, say, I think it's 3 in our hypothetical dreamland, but typically we don't, in this one we don't actually have a coefficient, so it would just be that amount. Okay, so now that we've figured this out, we know that this amount of potassium is going to react completely. So we can take this amount, this many moles, and we can carry it to the end. Now, we divided by 2 here, but let's just imagine we undid that and we have twice this number again. I'm going to erase all this fluorine. We figured out that we have excess fluorine, so now we kind of don't really care about it because we know we're going to have plenty to react. So if we go through this, that gives us, I think, about 1.125 moles of potassium. Now if we convert using ratios to go from moles of potassium to moles of potassium fluoride, we'll put moles of potassium here on the bottom, moles of potassium fluoride, and we just put the coefficients in the equation in for our little conversion factor here. 2 is the coefficient for moles of potassium, and 2 is the coefficient for moles of potassium fluoride. So those just cancel out. That's kind of nice. And then that will give us moles of potassium fluoride. After that, we'll just need to convert from moles of potassium fluoride to grams. We put moles on the bottom so that it'll cancel out. And then we put the molar mass of potassium fluoride up here on the top. That should be, let's see. What is this number? I think that's potassium again is 39.0. It's right there. I'm kind of blind. 39.098. There's only one potassium, so that's the number we use. And then 18.998 is the molar mass of fluorine, and there's only one. We times that by grams, and that, I believe, is our answer. Should be about 65.38 grams. If we were doing sig figs, we would just round this to 65 grams. And that's how you do a problem like that. That was our limiting reactant. Our limiting reactant was potassium because it ran out first. Now let's go back here. Now we'll talk a little bit about percent yield and actual yield. in theory, what we just talked about, that gave us the theoretical yield of potassium fluoride. It's like if the world was perfect and the reaction went all the way through, then we would produce that amount of potassium fluoride, the number that we calculated. I think it was 65.38 grams, right? That's our theoretical yield. If everything was perfect, the math tells us we should get that much. Now, because we have entropy and a lot of other reactions that can, a lot of other factors that can make a reaction not happen completely, oftentimes we'll measure a smaller number than this. So what if I told you that we had those same quantities at the beginning, the amount of potassium and the amount of fluoride, and then I told you that the actual yield was 45 grams. And then I asked you to calculate the percent yield. The percent yield, I think I wrote that backwards. I think that's what a percent symbol is. Percent yield equals actual yield divided by the theoretical yield. This is like, if everything was perfect, this is what we would get. And because it's a percent, we times it by 100. This should always be less than 100 and bigger than 1. It's a fraction. If it's negative or it's bigger than 1, that would technically mean you somehow produced more than was possible. That's kind of wild. You should not get an answer like that. So we did all the work with limiting reactants to figure out that this was our theoretical yield and this is our actual yield. We actually produced 45 grams of potassium fluoride. We put 45 over 65.38, multiply that by 100, that's our percent yield. I think that number is 68.8% yield. Hopefully that helps. I think we can go on. So, we're talking about chemical reactions. We have a lot more concepts right now and a little bit less math. So you may like that, you may not. It just depends. So I'm going to draw two types of reactions. And it's pretty important you know what these graphs mean and maybe even that you could duplicate them if you needed to. So let's say we have right here, on this amount we have energy, and then on this side we have time. And we're just measuring the energy of our reaction over time. Now every reaction takes a little bit of energy to get it started. This is called the activation energy. So we'll be starting over here, and then we'll have a little up, and then it will go down after. So that's an example of one type of reaction. The other one, with the same axes, energy and time, will look kind of like this. Right? In both places, this bump is the activation energy. That's probably too high. I doubt you can read up there. I should have thought of that. Let me just check real quick if you can see the top of that bump anyway. Yes, okay, we should be good. So, we know that there are two types of reactions. Some reactions that are exothermic and some that are endothermic. Exothermic reactions release heat, right? And endothermic reactions absorb heat. They feel cold because they're taking heat from your hands. That's an endothermic reaction. Same thing with exothermic. They feel hot because they're emitting heat and they're going into your hands. That's like hand warmers are exothermic reactions. They release heat. So if we look at both of these, this one takes some energy to get going, but its final amount of energy is less than when it started. That means it had to spit out that energy, right? It had to release it. This is an exothermic reaction. This one over here, now of course it takes some energy to get it going, the activation energy, but the final amount of energy it has is above where it started below, where it started at the beginning. This is an endothermic reaction. Now, if you wanted to, you could measure between the initial amount of heat that it has and the final amount of heat that it has, and you could look at the change there. Now, of course, there's a little bit more energy that you need at the beginning of a reaction, right? But that amount of energy then leaves again. So this amount doesn't really count. This is your activation energy. I'll just write E. But this amount you changed and you permanently changed, right? So this is like your delta H value for your reaction. This is the amount of heat that you absorbed because you're endothermic, right? You absorbed it. That means you needed it on the reactant side. You needed that heat to be input in order to do the reaction. Now, if you look over here, this is also a delta H value, but you lose that heat. In a sense, you had that heat at the beginning, and then you release it. So in a sense, like let's say we have reactants here, and then they go to form products. The delta H value is on the products side for an exothermic reaction. If we come over here, we have the same setup. We have reactants, products. Your delta H is a reactant. You need to input it in order to make the products. Hopefully that helps you visualize. These graphs we don't use them a lot when we calculate numbers, but conceptually they're really important. Remember what these look like. I would advise that. Okay, so let's do an example. Okay. So let's say we have a combustion reaction. We have, I guess, let's call it C2H6 plus O2. We know this is combustion, so we're making CO2 plus water. And just for the kick of it, I'll write in all the states. I think this is going to be a liquid. Little tiny liquid particles. This will be gas, and this will also be gas. Really quick, I know that this is not balanced as of yet. So to get the same amount of hydrogens on both sides, I would need to put a 3 right there. However, that means I'm going to have an odd number of oxygen on this side, and we can only have even numbers of oxygen on that side. So I'm going to multiply this by 2 so that we can have an even number of oxygens. So that'll give us 6 over here. That's going to give us 12 hydrogens on this side. Means we need a 2 over here. Then to get the carbons all balanced, I put a 4 right there. If I count out how many oxygens we have over on this side, we have 6 oxygens there plus 4 times 2, 8. That's going to give us 14 total oxygens. If we divide that by 2, we'll need 7 in front of this. And we know this is as simple as we can get because this is an odd number. Okay, so there's also a delta H value. You're burning something, so in a sense this is a fuel. It's nice to burn things because we produce energy. So we're going to have a delta H value over here. I'm just going to make up something. This is probably not accurate, but let's say it's 35 kilojoules. You could see a problem that would ask you, how many, I'll say question mark, how many grams of C2H6 do you need to burn in order to produce 200 kilojoules? We can use kilojoules in these reactions, just kind of like what we used mole ratios at the beginning, or a little while ago anyway. So let's say that we need 200 kilojoules. Now we know that for every 35 kilojoules that we produce, we need to have 2 moles of C2H6, right? So if I put kilojoules on the bottom, cancel it out, and I put moles of C2H6 up here at the top, then we'll put 35, this number right there, and then we'll put the coefficient of C2H6 right there. Now we're in moles of C2H6 because the kilojoules cancel out. If we want to go to grams, we'll have moles on the bottom, so moles will cancel out. Then the molar mass, which should be like 12 times 2 plus 1 times 6 grams, C2H6. And those cancel out. We should have our answer. I don't know exactly what it is, but it's 200 divided by 35 times 2 times, I think that's 30. I think that's 30 grams. That will give you your answer. That's how you would do an example problem with delta H values. This is your delta H value for this reaction. It's an exothermic reaction, which means you do the reaction and you produce extra heat. Again, that's different from activation energy. Activation energy is a little bit of energy you input to start the reaction, but it's given back to you. It doesn't really matter in the course of the long term of the reaction, right? It goes up and then down the same amount. It's different with the delta H. That's a permanent change in energy that you either absorbed or you released. Okay, on to the next concept. We have now, I think now we're in chapter 8. We got lots of gases and whatnot going on now. So we're going to talk about some different properties of gases. So we have a quantity called pressure. I'm sorry, I'm using a less good marker. Pressure is an amount that's just like, it's a force per area, right? Every gas will exert a pressure. Sometimes it's really light, sometimes it's not really light. Typically the pressure of just like your normal everyday usage is about 1 atmosphere. We're a little higher in elevation. I think the average pressure in Provo is about 0.8 atmospheres or something like that. So we'll have P. Every gas will have a volume, the space it fills up. There will be a temperature of the gas, T, and then there will just be the amount of the gas in moles. Now, what some relatively clever scientists figured out is that all of these are related. On your exam, you'll be given an extra equation sheet this time that will have some specific gas laws written on them. They're proportional to each other, right? So it's kind of like, if I take P, I think it's P times V. If you take the first pressure of a gas, you times it by the volume of that gas, then if you know the second pressure you have, then you can figure out what volume 2 is, right? Because volume 2 is just volume 2 equals P1 times V1 over P2. It's really convenient, actually, because then you only need to know a certain number of variables and you can figure out the rest of them. Now, because they figured out a few different laws, they kind of combined them into one larger law, right? So there's an ideal gas law. It's called PV equals nRT. Like this. They figured this out. All of these quantities we know about except R. If I solve for R, PV over NT equals R, it turns out that if you take any gas and you multiply the pressure of that gas times the volume of that gas times the moles of that gas times the temperature, it will always give you one specific number. It's a constant. It's always R. And R is given to you on your equation sheet. It should be something like 0.082058. I think it's in liter atmospheres per mole Kelvin. It has a whole ton of units. Don't worry about that. The units are just meant to cancel out the units of all these other quantities when we're just solving for one of them. So because PV over NT is always one number, if you wanted to, you could say that that's equal to the pressure, volume, moles over temperature of a different gas, or even the same gas at another time. So let's put a 1 in all the subscripts of these. We'll put a 2 in the subscripts of these. So, say if you know the first pressure, volume, moles, and temperature, and you know the pressure and the volume and the temperature of the second one, but you don't know the moles, you could solve for N2 with algebra and just figure it out that way. Another thing you can do is, this is really relevant, especially to your exam. Let's say that you're given a problem and some of these factors don't change. Like let's say the problem doesn't mention moles, or it just says it doesn't say that you lose any moles. Then N1 equals N2 because it's constant over the time period. If you divide by a number on this side and you divide by a number on this side, you could multiply by that same number on both sides and cancel them out. So because it's constant, it doesn't matter. If the temperature is the same on both sides, it's constant and you can disregard it. And then you can just use the quantities that change and plug in values for those. So I have a few example problems written down here. Let's see. So we're going to do, let's say you have P1 over T1 and 2 over T2. You have 5 atmospheres at the beginning, and your gas is at 35 degrees Celsius. And then at the end, something happens, and now your pressure is 3 atmospheres. What's your final temperature? We can write little labels next to these. P1 equals this, T1 equals this, P2 equals this. We're trying to figure out what T2 equals. Now we know that the moles don't change. We're holding those constant, so we can disregard those. Same with the volume, right? The volume doesn't change, or the problem just doesn't mention it. So we disregard those. Now we have P1 over T1 equals P2 over T2. So if we solve for T2, right, we have we multiply both sides by T2 and we get T2 times P1 over T1 equals P2. We divide by P1 so that we can get T2 by itself. T2 over T1 equals, P2 over P1, and then we times both sides by T1. So then we just have T2 on this side equals P2 times T2 over P1. Now, there's something really important that I haven't really talked about yet, is in order to use temperature with gas laws, you need to be in Kelvin and not in degrees Celsius. The reason why is, imagine that we were using like 0 degrees Celsius here, right? Like your gas was about freezing temperature for water. Now, if we looked at our original equation, that would mean we were dividing by 0. That's a mathematical no-no. We don't like that. It's bad juju. We don't do that stuff. So some guy figured out that there is a theoretical absolute 0, very bottom of the scale, and that all temperatures we see in the universe are above that. The measure from that 0 to wherever the temperature is, that's Kelvin. To get to Kelvin, this is on your equation sheet, just add 273. If you want to be super accurate, you add a 273.15. And that's how you convert from degrees Celsius to Kelvin. Now that we've got that out of the way, we can plug values in. So we have T2 equals 3 atmospheres times 35 plus 273.15 K over 5 atmospheres, right? That means our units will cancel, and we'll have some number that will be in kelvins. I think, did I write down that answer?
I have it as like around 185.
About 185, says my amazing editor again. So that's how you do a problem like that. You can do that with different quantities, just cancel out the ones that are constant. Now we'll do an example of like a PV equals nRT type equation. This is instead if we don't have different quantities of pressure, like a P1 and a P2. This is just we have one of them and we're trying to solve for one of the other quantities. So let's say that we have our pressure is 730 millimeters of mercury and our volume is 3 liters and our temperature is 280 Kelvin. And we're trying to figure out how many moles of gas we have. So we could solve this equation for moles just to make our job a little easier. N, we divide both sides by RT equals PV over RT. Now we have pressure in a different unit. That's not good. If you see pressure in anything but an atmosphere, when we use R, R is in units of atmosphere, so pressure also has to be in units of atmospheres too. Also be cautious with volume. When using PV equals nRT, R needs volume to be in liters and not milliliters or any other measure of volume. So convert volume to liters, convert pressure to atmospheres, convert temperature to Kelvin, and moles should be in moles. So let's convert this to atmospheres. This is in your equation sheet, but for every atmosphere of pressure, there are 760 millimeters of mercury. That uses kind of an outdated, I don't know if it's outdated per se, but when they were first measuring pressure, they had like a tube of mercury with a vacuum in this end. And then the pressure of whatever gas would push the mercury up the tube. And they could measure how far the mercury went up the tube. And that's why we have a measurement in millimeters of mercury, because they were measuring how many millimeters of mercury did the pressure push it. Right? So if we convert this to atmospheres, we divide by millimeters of mercury to cancel out the units. There's 1 atmosphere in that. That will give us some answer. Now we can plug all this into our equation to figure out what N is. So N equals 730 divided by 760, because that's just the number we figured out a little bit ago, ATM, times 3 liters over R, let's put temperature first. We have 280 Kelvin times 0.082058. That's the value for R. It's on your equation sheet. And then this has units of liters times atmospheres over moles times Kelvin. What you'll notice is because we're dividing by mole, because in the denominator we're dividing by moles, that's the same thing as timesing by moles, so it goes up to the top. And then we have liters divided by liters, those cancel. We have atmospheres divided by atmospheres, those cancel. We're dividing by Kelvin, and then we're dividing by Kelvin in the denominator, those cancel. The only unit we have left is moles. That's right. That's what we want in the end. So you can multiply this all out. It's this number times 3 divided by 280 times 0.082058, and we'll get the number of moles. I don't know what that number is. It's what?
0.125.
0.125. Sounds right to me. Okay, so that's how you do a bunch of gas laws equations. Imagine, just for a second, that they gave you a pressure, a volume, and a temperature of a certain reactant in an equation. Let's say, I think you said that was 0.125?
Mm-hmm.
Okay, I'm just going to write that over here. So let's say you have what gas do we want to make? I'm trying to think of an example off the top of my head. Okay, so let's say you have a balloon full of CO2. And then it decomposes and forms carbon plus oxygen gas. That's already balanced, pretty nice. And let's say at the beginning you have this pressure of CO2, you have this volume of 3 liters, you have this temperature, and then the question asks you, how many grams of carbon do you make? Well, we know how to figure out moles of CO2. That's just what we did, right? 0.125 moles. We used the gas law to get there. Now we can just use our typical mole ratios with equations to figure out moles of grams of carbon. For every mole of CO2, 1 mole, there's 1 mole of C. And then for every mole of C, there are 12 grams of C. And then we can figure out the amount of grams of carbon that we would produce. That's an example of like a gas law's equation. Gas law being used with an equation to figure out the amounts of grams of a product or a reactant. That's how you could use it together, because both of them share a number of moles as an important amount. Okay, let's keep going. All right, volume in moles. Avogadro, the same guy who figured out the number of atoms in a mole, 6.022, that thing, he was the guy who helped figure out that N was related to P, V, and T in this equation. So that's kind of neat. We did some example problems. Okay, let's talk about partial pressure now. So, a guy named Dalton, he also did some work with the atom that you may remember. He figured out that the total pressure of a system is equal to the partial pressure of each gas in the system. So that's like P tot equals P1 plus P2 plus P3 plus P4. These are partial pressures, right? And it's dot 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 to mean however many partial pressures there are. So this one might be a partial pressure of oxygen. This might be a partial pressure of fluorine gas. This might be a partial pressure of hydrogen, so on and so forth. He also found that the partial pressure of a certain gas, say PO2, is equal to the total pressure of the whole system times the mole fraction of oxygen. So the mole fraction is just kind of like the fraction of moles of oxygen over the total moles in the system. So let's say we have a system. There are, actually I wrote down some numbers. We have 5 moles of O2. We have 2 moles of nitrogen, and we have 1 mole of, I wrote down, of fluorine gas. And we know that our total pressure is 3 atmospheres. A question might ask you, what's the partial pressure of oxygen? So, to get our mole fraction, I'll just write down the formula for a mole fraction. XO2 equals N of whatever this gas is, right? Moles of that gas over N total, the total moles in the gas. So the mole fraction of oxygen would equal 5 moles over 5 plus 2 plus 1 moles. That equals 5/8 is our mole fraction of oxygen. Multiply that by 3 atmospheres, and that gives you your partial pressure of oxygen. Should be like 1.875 atmospheres. You can also go and figure out the partial pressures of these ones, right? The mole fraction of nitrogen in this situation would be 2 over 8 moles, because 8 is the sum of all of those, equals 1/4 times 3 ATM. That's just, I think, 0.75 atmospheres. Right? And then if you did this one, this should just be 1 mole of fluorine over 8 total moles times 3 atmospheres. And that gives you some number. That's point, I think, 375, 0.375. What you'll find is if you add this plus this plus this, you'll get three atmospheres. Pretty neat. We just did Dalton's law. So that's a good example of a mole fraction and a partial pressures question. That's pretty much all you need to know about that as far as I'm aware. Boop, 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 boop. Moving on. Oh, this is quite a video in terms of length. Now we're into solutions. I hope you're feeling good. We're getting close. So, solute and solvent. This is your solvent is whatever is dissolving the other thing. So water is typically your solvent, right? It's whatever's dissolving, like whatever you're putting in, like salt or sugar. Water is your solvent. Solvents dissolve. Solutes are the thing that it's being dissolved, right? So salt or sugar in those examples that I shared are typically solutes. They're being dissolved by water. Solutions are homogeneous mixtures. This means if you took like a tiny little sample of, like say we had a little glass of, say, salt water, and it was all completely dissolved in there. If we took like a little sample of this right here and we pulled this out, we would find the same amount of salt in that little section as we would over here if we measured that little part, right? That's what it means by homogeneous mixtures. If it was heterogeneous, this is maybe if something isn't fully dissolved, kind of like your hot cocoa. If you don't stir it well enough, you get like a big old clump of something floating in there. That's a heterogeneous mixture. It's not fully dissolved. If you took a sample of just that clump, that would be super different than a sample of like this part over there. That's a heterogeneous mixture. It's not a solution. So water is polar. That's really important. It's really convenient that water is polar for a number of reasons. But what that means is if you dissolve a substance that is polar and you put it in water, it will dissolve. Water will be able to dissolve things that are like it. So polar things dissolve other polar things. Now, that's not true with, say, like, if you put a non-polar thing, like oil, in water, water cannot dissolve it because it's polar. Polar things cannot dissolve non-polar things, and non-polar things can't dissolve polar things. So let's say you have we have, I think this is ammonia right there. If you were to draw the Lewis structure for ammonia, you would get a lone pair right there, and a hydrogen here, hydrogen there, hydrogen there. This is going to form a polar shape, right? There's an imbalance of charge with this lone pairs. Ammonia would be able to dissolve in water. Same thing with like ions, right? Ions are super polar. Like, say you have sodium chloride. You have sodium here, and you have chloride over here. There's super negative charge over here and a super positive charge on this side. Water will be able to dissolve that, split them up super easy. But say you have something like methane that we were talking about before, right? CH4. This is a non-polar molecule. Water would not be able to dissolve this. That's important. Remember that. That will come in handy later. So now we're going to talk about electrolytes. Electrolytes are ions in solution. So let's say you dissolved sodium chloride, right, in water. The ions in this ionic bond will separate from each other. This is called dissociation, dissociate. So we'll have Na plus Cl minus plus H2O. If you were writing in states, H2O is a liquid. And because H2O is on the same side and doesn't change, most of the time people just leave that out. So in a sense, I'll do that myself. I'll just say NaCl at the beginning dissociates into sodium plus, and chlorine minus. If we write in the states for those, that's AQ, which means they're dissolved in solution. It's called aqueous solution, and that's why it's AQ. And over here, this is not dissolved, this is just a solid. That's what those symbols mean. Now, electrolytes are when ions dissociate in solution. So like Gatorade has electrolytes, and what that means is they have floating ions that are separate like this. This, because there's imbalances of charges and electrons are more able to move, this means electrolytes conduct electricity. If something is dissolved in water but isn't an ion, it's not going to conduct electricity. So like sugar, right, is C6H12O6. If we dissolve that in water, that doesn't split into ions. It just stays as the same molecule. Sugar is not an electrolyte. It does not conduct electricity. Now there are some other things, like I think hydrofluoric acid is a great example. If you put this in water, some of the molecules of hydrogen fluoride, some of them will separate. So you'll get some that will be H plus and fluorine minus. But not all of them will. Like a bunch of them will stay together because they have a pretty strong bond. So this, because this does not produce all of them don't dissociate, this is an example of like a weak electrolyte. So sugar is not as a non-electrolyte, right? Hydrofluoric acid is a weak electrolyte because not all of them will separate, dissociate in solution. And sodium chloride is a strong electrolyte, which means all of them will separate in solution. When they're dissolved, all of them will separate. This one will conduct electricity great, the strong electrolyte. This one will conduct electricity weakly, it's a weak electrolyte. This one will not conduct electricity, sugar. So, let's see, I think we can move on here. Equivalence. So, an equivalent is like a measure of a mole of charge. So let's say that in this example, we dissolved 1 mole of sodium chloride. And then somebody asked us, how many equivalents of positive charge do we have at the end? Because it asks us about positive charge, we only look at sodium because chlorine is negative, right? For every mole of positive charge, that is 1 equivalent. So we would say we have 1 mole Na plus, and in each mole of Na plus, we have 1 equivalent. Looks like that. You might see units that are like milliequivalents. That's just using a prefix to say it's like 1,000 times smaller than 1 equivalent. Now, if we have an ion with a different charge than 1, we have pretty much that charge it really affects the equivalence. So if we have, say, calcium, let's say calcium fluoride, and this dissociates in solution, so we have calcium 2 plus and fluorine minus, and we have twice as many of those, right? And we have 1 mole of this at the beginning. Let's say we have 2 moles. It makes the math a little bit better. 2 moles. So now, if they ask us how many moles of positive charge we have, we take our original amount, 2 moles of calcium fluoride. And for each mole of calcium fluoride, I know that I have 2 plus charge, right? So for every mole of calcium that I have, I'll get rid of this. Right, we have 2 moles of calcium from this equation at the beginning. For every mole of calcium, we have 2 equivalents because this is a 2 plus charge. This number of equivalents will depend on the charge. If it's a 3 plus, calcium is never a 3 plus, don't worry about that. We would have 3 equivalents. The same thing if it's negative, right? If this is like a 3 minus charge, equivalence doesn't really care about what the sign on the charge is, it's just about the number. So 3 minus, that would be 3 equivalents per mole. So if we times this out, 2 equivalents, we have 2 times 2, we'd have 4 equivalents of positive charge. If they asked us how many moles of negative charge we have, so we have 2 moles of this at the beginning, and for each mole we have 2 fluorines, so 2 mole CaF2 times 1 mole CaF2 is 2 moles of F2. And then fluorine has a -1 charge, so for each mole of fluorine, sorry, I should say this is 2 moles of just F, no subscript there. 2 moles of F. For each mole of F, we have 1 equivalent. All of our units cancel out except for equivalent. Do 2 times 2 equals 4 equivalents of negative charge. So we have 4 equivalents of positive charge, 4 equivalents of negative charge. If we wanted to know the total equivalents, that would just be those 2 together. That's 8 equivalents. You can convert this again to milli if you want. That's just like for every 1 equivalent, there's 1,000 milli equivalents. And you could go backwards by doing the similar thing by just swapping that ratio. Okay, I think that's enough about equivalence. We're going to keep moving on because, oh boy, we've been here for a while. Let's talk about solubility. So if something says, if a problem says the solubility of a certain substance is this by this, that means that's the maximum amount of solute you can dissolve in that much solvent. So if the solubility of sodium chloride in water is 150 grams of sodium chloride in 100 grams of water, that is the maximum amount of sodium chloride you could dissolve in 100 grams of water. In a sense, if you tried to dissolve any more sodium chloride in there, it would just sit as a solid at the bottom. It would not go into that water. They were completely surrounded by water molecules, and the water molecules cannot surround any more molecules. They're done. And essentially, that's what's happening when you dissolve something, is your polar water molecules will surround an ion or a polar molecule and separate it from other ions or other polar molecules. That's what being dissolved is. And if something is saturated, it cannot do that anymore. It has no more space. So, in theory, you could figure out, let's say that you had 75 grams of water, and you were trying to dissolve 130 grams of salt in there. Would all of those grams of salt dissolve? We can figure that out. So let's start by doing 150 grams of sodium chloride over 100 grams of H2O. We simplify that, we get 1.5 grams of sodium chloride per gram of H2O. That means for every gram of water that we have, we can dissolve 1.5 grams of sodium chloride in it. If we then take our amount of water here at the beginning, 75 grams, we times it by this number. This will give us the maximum amount of sodium chloride that we could dissolve in 75 grams of water. I think that gives you an answer of like 115-ish. Is that right?
I have 112.
112, that sounds right. 112 grams of sodium chloride. So if we then compare this value to the value we had at the beginning, say we're trying to dissolve 130 grams of sodium chloride, the maximum amount that we can dissolve is this much. So we will, in a sense, have dissolved 112 grams, and then we'll have 130 grams minus 112 grams of sodium chloride just sitting at the bottom. I think that's 18 grams. So 18 grams will not be dissolved. You can do this backwards, forwards, in some different ways, but those are the concepts, and that's how you do problems like these. Technically, solubility is a kind of concentration. A concentration is like a measure of amount of your solute divided by your solution. So let's look at some different ones. We have mass, sorry, I'm going to use the good marker here. Mass over mass concentrations, mass over volume concentrations, we have volume over volume concentrations, and we have moles per liter concentrations. These ones are kind of special. They get their own symbol. It's big M. If you see big M, that means molarity, which means moles per liter. We're going to talk a little bit, we're going to backtrack just a little bit. I want to talk more about solubility actually. So if you add temperature, that can change your solubility, right? So let's say you have a solid, like sodium chloride. If you heat the sodium chloride, that will make it more soluble. Heating makes solids more soluble. This is because you add energy, and it's easier to break the bonds between the solid molecules so they can dissolve into water a little bit more easily. So if you raise your temperature, that will increase the solubility of a solid. If you lower temperature, that will decrease the solubility of a solid. The opposite is true of gases. Gases, as molecules, are already bouncing around really fast. If you give them more energy by raising the temperature, that will mean they'll bounce around faster. And it's harder for water to surround them when they're moving around so fast. And the gas will just like come right out of the water. It's moving so fast. So if you raise the temperature of a gas, you decrease its solubility, its ability to be dissolved, right? You're able to dissolve less gas at higher temperatures. And if you decrease the temperature, you increase the gas's solubility. So it goes in opposite ways between gases and solids. Hopefully that is helpful. Let's see. We can talk really quickly about a double replacement reaction. Let's imagine that we have, I think, potassium nitrate plus silver fluoride? Sure, I think that dissolves. So we have K plus plus NO3 minus plus Ag plus fluorine. I kind of wish I had a different example for this with more coefficients. Let's change some things. Hang on, stand by. I'm pulling up some examples. Okay, we're changing things up. Let's say you dump some potassium phosphate and some silver nitrate into some water, and you let it dissolve. Right? So if I were to write the equation like this, K2PO4 plus AgNO3, they react. This is a double replacement, they swap. K has a positive 1 charge, nitrate has a negative 1 charge, so it's balanced like that. The formula for the other one, that's going to be Ag, I think 2 for PO4. As far as I remember, phosphate has a negative 2 charge. If we balance this equation really quick, we have 2 potassium here, we need a 2 right there. That means we'll need a 2 right there, and then that should be balanced. Now, if we dissolve it in water, what happens is all of these separate into ions, right? So we have 2 potassium ions for each of these, so we'll put a 2, then a K, and then plus, because it's an ion, it has a charge, plus PO4, 2 minus, and this one doesn't have a coefficient because there's just one of them in there, plus, and we have a coefficient there, so we have 2 Ag, plus, and we take the coefficient from the whole molecule, we apply it to nitrate, 2 NO3 minus, react. I'm just going to write the product side a little bit lower here. 2 K plus 2 NO3 minus. But then, if you look at silver phosphate in your solubility chart, which will be given to you on the exam. Know how to read that. If you have any questions about interpreting that chart, just email me or any of the other TAs. You'll notice that phosphates of silver are insoluble. So that means that this will become a solid, Ag2PO4. This will be a solid and it won't be dissolved. They'll react and form a solid. This will precipitate in the solution. That's what that word means. So in a sense, this is our complete ionic equation. We have considered everything. Everything is balanced. All the coefficients are just as they should be up here. We're feeling good. Now you might notice that potassium is the same on both sides and nitrate is the same on both sides. In a sense, what we can do then is consider them gone. We'll just get rid of them. That means this is our net ionic equation. We just have the stuff that changes. Phosphate and silver, and then silver phosphate here at the end. That's what that looks like. So this is your net ionic equation. Before we crossed everything out, that was your complete ionic equation. Make sure that everything is balanced and that, say like silver and nitrate, they should have the same ratio as they were when they were together, like we did the equation up here. Okay, we're gonna move on and we're gonna go fast because this is a long video. Okay, so we got concentrations and dilutions, and then we're gonna talk about a few things, but we're almost there, almost there. So these are all in units of, I'll write the units next to the concentrations. Again, we have the mass over mass, mass over volume, volume over volume, and moles per liter. This will be in units of grams per grams. This will be in units of grams per milliliter. This will be in units of milliliter per milliliter. And then this will be again in units of moles per liter. These are all solute, so like sodium chloride or sugar, over total solution. That means your water plus whatever. Okay, sorry there. The video cut out. Turns out I've been talking for an hour and 37 minutes. Okay, moving on. So we have an equation. This is C1 times V1 equals C2 times V2. These stand, volume is V, of course, and C stands for concentration. Typically in units of molarity over here, moles per liter. So, hang on, I'm just gonna check really quick that it's still running. Yeah, we're good. We have 4 minutes to record the rest of this, so let's get going. So if we have, for example, our solution has 3M at the beginning, and then there are 5 liters of it. At the end, we'll have, and let's say at the end we have, say, 8 liters. What we can say is 3M times 5L equals, I'll put X as our variable, M, times 8 liters. We solve this for X, that's going to be 15 over 8 equals X in units of molarity, which is just moles per liter, right? And that's how we can use that equation to solve for concentrations and volumes. Okay, let's keep going. We're on the last page now. Okay, we're going to get there. So, solutions are dissolved substances. If we compare this to like colloids and suspensions, pretty much just be aware that colloids have slightly larger particles than solutions do. So like Dr. Watt in his example in lecture, he shined a laser through the solution, and even though it looked clear, there were particles in the colloid that deflected light. So if you shine a light through something and it deflects light, you can see the light in the solution, then that is a colloid. A solution will not do that. Suspensions are even larger than colloids. They have like particles that are floating that are bigger than colloids. So like imagine you got sand and you mixed it with water in a jar, shook it up. That's like a suspension. They're really large particles. So suspensions have really large particles, and you can separate them from water using a filter and sorry, what's the word? A semi-permeable membrane. A colloid filter won't work, but you could separate it with a semi-permeable membrane. And then a solution you couldn't separate even with a semi-permeable membrane. So if you add an amount of a solution to, I'm sorry, my brain is flustered. Let's say you dissolve a certain amount of something in a solution, that will affect its boiling point and its freezing point. The reason why is, let's say you have water, right, and you're trying to freeze it. That means the water will form all of these crystals, like this. Now, if you dissolve something, that's like a particle that's getting in the way of this crystal. That means it will be less able to dissolve, meaning that you'll have to remove more heat, more temperature to dissolve it. This lowers the freezing point. Hello, the video cut out, and so here we are again. I freed up some space on my phone, so it should be good to go to just go right to the end. Okay, the reason why dissolving some solute in, say, water, the reason why that affects the boiling point is because it makes water less able to escape the liquid phase to enter the gas phase. So like, let's say that these are particles of water, and they're in a kind of liquid formation. Imagine they're kind of jumbled, they're bouncing around, right? Now, in order for water to become a gas, these have to escape the packed area and start bouncing around in this area up here. But now, let's say that some of these particles, instead of being water, they're instead dissolved bits of solution. So we could say this is a sodium ion, or this is a fluorine negative ion. This kind of blocks water's ability to become a gas, meaning it lowers its vapor pressure, which means it takes more energy to get all of the water here to boil and leave the solution. So that's why dissolving something increases the boiling point, and why dissolving something in that water also lowers the freezing point. Now we have an equation to measure exactly how much that is. We have delta T equals K times moles, I think it's moles of solute. So the symbol for that is N solute, over mass of water, right? Now K is just a constant that measures, like, it's a ratio. So K for freezing is on your equation sheet. It's negative 1.86 degrees Celsius. I think the units are kilogram over mole. This is so it cancels out these units. Now the K value for boiling, I believe, is 0.51 degrees Celsius per kilogram mole. So if you're talking about the freezing point, you're going to want to use this K value in your equation. Now if you're talking about the boiling point, you'll want to use this K value. So let's say that we have 5 moles of sodium chloride, and we have 1 kilogram of water, and we want to know how much the boiling point will change. Or what's the new boiling point of the water, I should say. I'll say new BP question mark. Something that's important is this amount right here, this moles of solute. This is total moles of particles. Now when we dissolve, say, like ionic substances, like sodium chloride, this will split up into more moles than just 1 mole of the formula. So let's talk about some examples. Let's do okay, so potassium chloride here will split into a potassium ion and a chlorine ion. So if you have 1 mole of this, let's call it 2 moles, right? 2 moles of each of these substances. That means we have 2 moles of sodium ions and 2 moles of chlorine ions. That's 2 times the number of moles that one of those will make, like the number of particles that one molecule will make. So 2 times 2, we'll have 4 total moles. Now if we look at magnesium hydroxide, this is going to be a 2 right there. That's a wrong formula. But so this will split into 3 particles, right? We'll get 1 magnesium particle and then 2 hydroxide particles, right? In polyatomic ions, they stick together as 1 particle, so it doesn't split into like oxygen and hydrogen. It's just hydroxide, and we have 2 of them, so that's why we have 2 particles. So if we want to find the total number of moles of particles, we would do 2 times 1, 2, 3 equals 6 total moles. For this one, we're going to end up with 3 particles of calcium and 2 particles of nitrogen, so 5 total particles. So 2 moles times 5 equals 10 total moles of particles. This is potassium hydroxide. Remember, this is again, let's call it nitrate, just another of the polyatomic ions. This will again just split into potassium, and nitrate, because it's all 1 polyatomic ion, will stick together. Should be putting the charges on these. So we'll have 2 moles at the beginning times the number of particles it splits into, 1, 2, equals 4 total moles of product. So if we come over here and apply this to this equation, we have 5 moles of sodium chloride at the beginning. We know sodium chloride will split into 2 particles, so we'll do 5 times 2 equals 10, and that's N. We have 1 kilogram of water. That's pretty convenient. That's just the mass of water right here. So 1 kilogram equals M. This is important for this equation. You need to be in units of kilogram, or whatever units K has. K has kilograms and it has moles. So if they gave you an amount of, say, grams of sodium chloride, you would have to first convert that amount of grams of sodium chloride to moles using the molar mass, and then multiply it by how many particles it splits into, and then that would be your answer in moles. So now we can plug this in. Because we're concerned about boiling point, we'll use this K value. So we'll do 0.51 degrees Celsius times kilogram over mole times 10 moles divided by 1 kilogram. The kilograms and the moles will cancel, and we'll have an answer in degrees Celsius. This equals our delta T, right? This is our change in temperature. This is not our final answer if they're asking for the new boiling point. We have to add this amount to the already known boiling point of water, which is 100 degrees Celsius. So if we do 100 plus this number, let me figure that out. It's just 0.51 times 10. That's just 5.1, right? The new boiling point of water of this solution is 105.1 degrees Celsius. Now, if we wanted to find out the same thing for freezing, we would just put in negative 1.86 here, right? This would give us delta T equals negative, just times that by 10. I think that's negative 18.6 degrees Celsius. Now you add that to the freezing point of water, which is 0 degrees Celsius, right? So 0 degrees Celsius plus negative 18. So that's just going to be 0 minus 18.6 degrees Celsius. Your new freezing point is negative 18.6 degrees Celsius. Hopefully that makes sense. I think it's not too bad once you get the hang of it, and once you understand that different things will split into different number of particles. If the the molecule that you're dissolving is something like sugar, right? Like let's say we have 2 moles of C6H12O6, like this. If we dissolve that, that's not going to split into ions or anything like that. So this, in a sense, will just produce 2 moles of particles because it just won't split. So we'll have the same amount on both sides. Hopefully that makes sense. Okay, we're almost there. Let's see, what else do we have to cover? Okay, so the last thing we have to talk about are different types of solutions and how they can move across semi-permeable membranes. So let's say this is a semi-permeable membrane, meaning that some particles will not be able to move across it, but water will, as a matter of fact. Now let's say that we have different concentrations on different sides of this membrane. So let's say we have, let's just say it's salt. We have sodium chloride. And I'm going to draw in a bunch of atoms, Na plus. I'm just going to check that you can see that really quick. My marker is dying. You can kind of see it. Hang on. Okay, this is great. We'll use this marker. So we'll draw in a bunch of ions in here. And then we'll draw in a few over here, but not as many. Right? There's more of the solute on this side of the semi-permeable membrane. Now we have a bunch of water here as well, right? Sorry, that should be an H. And there's a bunch of water over here on this side as well. Okay, so we can start to talk about some words that just compare concentrations. So if we were looking at this, there is a much higher concentration of solute on this side as there is over here, right? Like there's less sodium chloride per water on this side, on this side than that one. Like there's a bunch more water over here relative to sodium and chloride over here. Like it's almost 1 to 1 over here. And like 1 to 3 over there. So this is a specific type of solution. We have 3 words: isotonic, hypotonic, and hypertonic. These compare concentrations on different sides of the membrane. So isotonic means it's the same on both sides. Everything's chill. Water is maybe going back and forth over this membrane, but it's going back in equal amounts, right? Everything's fine. The sodium and chloride can't cross this membrane, but the water can. So isotonic means it's about the same concentration on both sides. Now, hypotonic, on the other hand, let's see. So a hypotonic solution, it's going to encourage the water to come to it. So let's say this side is hypotonic. That means it has a higher concentration of solute in the solution than the other side. What that means is water is going to want it to be the same concentration on this side as it is on this side. So a bunch of the water molecules that are over here are going to cross that semi-permeable membrane in order to get like the ratio of sodium chloride to water to be about the same on both sides. Even if it means in the end that there's more water on this side of the semi-permeable membrane. So a hypotonic solution will have a higher concentration of NaCl per water, which means it has a lower osmotic pressure, which means water will come into it. If this is like a cell over here, and this is say like the stuff it's floating in, right? Water will flow into the cell will swell larger, and it might get so large it pops. That's dangerous. You don't want that to happen. That can happen if you have a hypotonic solution. So let's now instead say this side might be hypotonic. If we come over here, and now we pretend that this side is the cell wall. Like let's say this half is the cell and that's outside. This side is hypertonic. What that means is it has a lower concentration of solute per water, right? And then the other side, which means that the water is going to want to leave the cell, exit, so that it can make the concentrations the same. So that means we're going to get a bunch of water leaving, which means if this is the cell, it shrinks. It becomes a lot smaller. It can get so small that it dies again. So that's what a hypertonic solution is. This has a higher osmotic pressure than that side. So just in review, isotonic, all good. Same on both sides. Hypertonic, water will come in. Lower osmotic pressure. And higher concentration of like moles NaCl or whatever it is per liter. And then hypertonic, oh, you probably can't see any of this. I'm sorry. It's useless that I'm writing that. But water, same on both sides. Hypotonic, water will come in. It'll swell. It has a lower osmotic pressure and has a higher concentration of solute. Hypertonic, water will leave. It has a higher osmotic pressure than its surroundings, and it has a lower concentration of moles of salt or whatever it is per liter. That is those three words and what they mean and their applications. I think that's it, everybody. I hope you enjoyed and this is useful to you. If not, I'm sorry. But yeah, I hope you do well on the test. It's going to work out great.